Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss the concept of Euler equation of motion and also we'll derive the Bernoulli's equation from this equation of Euler's. So before going to derive this Euler's equation of motion, so let me give a brief introduction about this Euler's equation and I'll just inform some application regarding this. Then we'll move to the Bernoulli's equation. So here, this Euler's equation actually it describes the rotational motion of a rigid body. We can consider a rigid body and it will be describe the rotational motion of a rigid body. And next is this concept Euler's equation, it came from the fluid dynamics, or you can say this is the fundamental principle of fluid dynamics. Fluid dynamics. Okay, this is one point and this is another point, you can say. Now the next thing is we need to, the Euler's equation, it will be considered for a steady flow. It will be considered for a steady flow. So steady flow, already we have seen in the previous lectures different types of flows. When you have studied there, it is described steady flow when the velocity with respect to time will be 0. And next is this should be considered for an ideal flow. So ideal flow means where the velocity, that viscosity of the flow or viscosity of the fluid will be 0 because it is an ideal flow, not a real fluid. Okay, so here viscosity will be not there, and we can consider some other assumptions are there like incompressible fluid. So these are the two things, major things we need to consider here. The next thing is this Euler's equation of motion will be give a relations. This will be give a relations between the velocity, pressure and density of a moving fluid. So suppose we need to consider a moving fluid. So this relation will be, this equation will give a relation between this velocity, pressure and density of that. Okay. And when the fluid is in moving condition, we need to consider the fluid should be in the move in the streamline condition. It should be move in the streamline path. Okay. This is one concept. Next is this Euler's equation of motion is based on the Newton's second law of motion. Newton's second law of motion. Okay, these are some points are there. Now I'll tell you the application of this Euler's equation of motion. It shortly just I'll tell you. So few applications are there. We can apply this concept in the area of aerodynamics. Now in the aerodynamics, what we can use in the area of aerodynamics, while we can identify the behavior or structure, we can say when we design a aircraft, to identify the behavior of a aircraft, we need this concept. Okay, or also when the aircraft, suppose when it is in the working point or the product when it will be working condition, then we can identify what is the lift force of that and what is the drag force is acting on that and what kind of other forces, aerodynamic forces related, we can also see in this concept. And similarly, one more example is there, that is hydrodynamics. So in the hydrodynamics also, we can analyze the motion of a fluid. Hydrodynamics. Here we can identify the analyze the motion of a fluid and also any kind of liquids we can see there, and also we can see the sieve design and analysis also can be done in this, in the hydrodynamics. Now apart from that also one more is there, turbo machinery. In the turbo machinery we can apply this concept of this Euler's equation of motion, okay, to do the design and analysis of components. Which kind of components? Now such as suppose a turbine is there, or any kind of compressors is there and turbine is there. To when you design this part and you can do some analysis on that, then we can use this concept of this Euler's equation of motion. And also we can use in the gas turbines and jet engines also this concept. Even in a CFD analysis also we used to consider this Euler's equation of motion. So these are some applications are there in this Euler's equation of motion. So after this, now what will go? We'll move to this equation, derivation of this equation. Okay. So now to derive this equation, first of all, I'll consider a liquid or a fluid which is moving in a streamline condition. As I told that this is we need to consider the fluid when it is moving condition, it should be considered in a streamline. So here I have taken a liquid here. This is the liquid part is there, or fluid is there. The fluid I have taken in a shape of cylindrical shape. Here I have taken the fluid which is in a cylindrical shape. Okay, and the fluid is moving in the S direction. Suppose some direction is there which is not X, Y, Z, some S direction it is considered. Okay, and the fluid is moving in, one more thing, the fluid is moving in the S direction and streamline, that need to be considered. Okay, the fluid is moving in the streamline and S direction, these things. And the size of this, the length of this fluid is ds. ds is the length of the fluid, and dA the cross sectional area of the fluid. dA is the cross sectional area of the fluid element. These two things. And now this equation, actually we need to consider the forces due to the gravity. You can consider the force. One is due to the gravity, another one is pressure force. Gravity and pressure, it need to be considered for this. Okay, so now in this cylindrical object, as I told, one thing is dA is the cross sectional area of the fluid element, another one is ds, the length of the fluid element. Okay, now what we need to find out here, the forces which is acting on the cylindrical element, that need to be identified. The forces acting on the cylindrical element. This is the cylindrical element, what the forces are acting. Now here, as I told, the pressure need to be considered and gravity need to be considered for this. So now, first thing, the force which is acting at this point, at one end of this cylindrical object, suppose this is the bottom part, at this bottom, what the force is acting here. Now here if you see, there is a pressure force is acting at this portion or at this area, and which is in the direction of flow. So because this is the direction of flow, at this direction you can see the arrow mark here. So this is the direction of flow. So the pressure force, I can write the pressure force in the direction of flow. In the direction of flow, I can write. So we know that pressure equal to force by area, and I can write the force equal to pressure into area. So here area is nothing but the cross sectional area of the cylindrical object. So the pressure force in the direction of flow, I can write P into dA. This is the cross sectional area of the fluid element. Similarly, second point I can write the pressure force, another one pressure force in the opposite side, which is opposing the fluid movement. So this pressure force will be slightly more than this object, because see, some pressure is acting here. If you go to some distance, that means some ds length it was crossed. Okay, so definitely there is some additional pressure will be acting on that, which is opposing to the movement of this direction. So that flow will be reverse. So the pressure force which is acting opposite to the flow, the direction what I have given, that means the reverse. This is the forward direction, this is the reverse direction, that's why given. So here what will be the extra pressure will be applied here in this condition. Now one pressure which is acting here, that is P, plus in this small cylindrical object there is a del P by what is the area, that means what is the distance covered here, that is del S into the total length of this, that means ds, you can write, and the area, cross sectional area. This is the pressure actually. This is the pressure which is acting on this total from here plus this side, and dA is the cross sectional area of the cylindrical object. So these are the two forces, pressure forces which is acting on the fluid element. Apart from that, another one pressure force, another one weight is there, that weight of the fluid element, because every individual having some weight. Okay, so that weight, we know that always the weight is vertically downward direction. So if I draw this one here, suppose this the movement is there. Now let me draw this. This is the center point of this, suppose. So weight will be always vertically downward. So that is W. So I can write weight of the object is, weight of the fluid element is W. So that can be written, we know that W equal to mg, mass of the fluid into gravity. Now here I can write, we know that also one more thing, density equal to mass by volume. And here I can write mass equal to rho into volume, density to volume. Now volume of the fluid element, so volume of the fluid element, how to calculate? So that we can calculate V place, we can write what is the area of that object, that means dA, into, we can write the length of that fluid element, that means rho into dA into ds. So it's the same value I can put it here. So rho into g into dA ds. This is the weight of the object. See, the weight of the object I have shown here in this direction, correct? But the fluid is moving in this direction. So there is a angle formation happened between this direction of flow and the weight of the fluid element, that is theta. Okay. Now, these are some forces which is acting on this fluid element. Now what I'll do, we need to find out the resultant force. We can say the resultant force on the fluid element, the resultant force on the fluid element in the direction of flow, in the direction of, in the direction of S, that should be equal to the mass of the fluid and acceleration in the same direction. That means the summation of force, you can write the mass of the fluid element into acceleration of the fluid element in the same direction of the S direction, suppose that is S. So that's why I written summation of Fs equal to m into As, acceleration of in the same direction. Now what I'll do, I'll just put all this value here in the summation of S. This is one pressure force, this is one pressure force, this is weight. Okay. Now, so P dA, and you can see this is one direction in this moving direction and this is opposite direction. So I can write minus of P del P by del S into ds whole bracket dA. Now another one W. W also, it is vertical downward. If I consider in the direction of this fluid, that means it is opposing to this one. So that will also come in this opposite direction. So now if I resolve this weight of this fluid in this direction of fluid and opposite to this one, that means x direction and y direction if I consider. So I need to consider W cos theta here. So what I can write, that is minus the value rho g dA into ds cos theta equal to mass into acceleration. Mass into acceleration, mass value already I told you, this is the mass value. So that is nothing but rho dA ds into acceleration a into as, not a into s, as, acceleration in the direction of s. So this is the equation. Okay, I hope you understand. This is the equation. Now what I'll do, I'll consider this acceleration which is in the direction of s. Let me write acceleration in the direction of s. So I can write acceleration equal to, we know that that is velocity with respect to time. So how to calculate the acceleration of the fluid? We know that this is velocity with respect to time. So here if you see, the velocity is a function of, you can say one thing, velocity we can say also, that means what is the distance traveled with respect to time. So the distance in the sense which direction it is moving. So the velocity we can say is a function of s and t. Velocity is a function of s and t, because here if you see acceleration is the remaining part is as usual is there. Now if I solve this one, I can get one equation. I'll solve that one later. Then first let me tell you this acceleration part. Now this one acceleration I can write in this way, in this format. Now same thing again I can write, as velocity is the function of s and t, like space and time. or in the kind of direction and time, you can say. So this one also I can write this dv by dt. I can write dv by dt. I can write del v by del t. Sorry, first we'll take with respect to s. Del v with respect to del s into, we can write ds by dt plus, we can write what, del v, again same del v with respect to dt into dt by dt. This is the equation actually I have taken for this, correct? But this equation I have written in this format or in this way based on the chain rule, okay? Based on the chain rule, or we can say that is the law of derivative also, we can say in that, or we can say that is the chain rule formation. So it is easy. So here see dv by dt given. The dv by dt I just written in this format. You see, if you cancel this ds, it will be cancelled, dt will be cancelled, only dv by dt plus again same thing dv by dt will be there. So just I have elaborated this one. So these things what I'll get here, dt by dt will be cancelled here, and if you see ds by dt is nothing but v, velocity. We know that ds by dt is v. So these things what I can write again, v del v by del s. V where it came? Now from this ds by dt. V equal velocity equal to ds by dt, we know that. So we can write v into dv by dt. And dv by dt for steady flow, we know that for steady flow dv by dt will be 0. So this portion I can make it 0. So I can write this one on behalf of acceleration part. Correct. Now same thing what I'll do, I'll just put in the equation here. Okay. Same value I can just put it here. Now we'll go to the next slide. Okay, before going to next slide, let's see PDA. Okay, let me write that equation again. Here PDA minus, again I just elaborate this equation. Again it will come PDA minus del P by del S ds. Yeah, del P by del S ds dA minus rho g dA ds. Yeah, minus rho g dA ds cos theta equal to mass into acceleration. So mass is nothing but rho g rho g will be not there, only rho dA dz, and we'll get the value of acceleration. We can put it, that is v dv by ds, suppose. Okay, so this is the equation. Now what I'll do, I'll cancel this equation, automatically will be cancelled. Next what will be there, minus dp by del p by del s ds dA minus rho g dA ds cos theta equal to rho g. Okay, this is the value. Now what I'll do here, I'll just put the divide a equation of rho ds dA in both side, this side as well as this side, right hand side, left hand side. So if I divide this rho ds dA, now see first one will come to here, so that will be here. What will be there here, cos theta, and that will be here. Okay, let's see. One more thing, 1 minute. That is minus of this. Yeah, it's correct. Next what will write, let's see, rho ds dA. So rho ds dA means ds dA will be cancelled. So what we can write here, minus del p by rho ds. Rho ds dA I have divided every side, both side. So I'll get, after cancelling this one, I'll get del p by del s into by rho. And next here again we'll get the value of g cos theta minus, again it will be cancelled here, rho g ds dA, rho ds dA cancelled. So what will get, minus g cos theta minus cos theta equal to, what will get here? Again, see, this part total is going to cancel. So what will be there? Only v dv by ds. Del v by del s or dv by ds we'll get. Okay. Or what we'll do here next, I'll take this term, this 2 term to other side, so that this minus term will be going to be positive term. So what I can write? Del p by rho ds plus g cos theta plus v dv by ds equal to 0. I hope you understand. This 2 term I have taken to this side, and this side will be 0. So I have written this one at this side and 0 other side. Okay. Now this is the term what we are getting here. Now if you see this cos theta is there, that need to be neglected here. So what I'll do, I'll go to the diagram again. Now for this diagram, if you see, again I have drawn one small diagram here that I have taken from that. That means when this angle formation happened, that is the distance of, if see, ds distance is there, and when the vertical it is downward, okay, now there is a angle formation happened here. Okay, now this cos theta, as I told, this is the cos theta side is there. Now if I want to write the cos theta, so for that particular triangle, let me draw here. This is the theta, and this is the ds, and this is dz, correct? So now what I can write here, cos theta equal to, I can write BC by, if you want to write this ABC angle, ABC, so cos theta I can write dz by ds, this one, dz by ds. So here in the value of cos theta, I can put the value of dz by ds. So that will be, give you the equation, yeah, plus g dz by ds plus v dv by ds equal to 0. Now if you see, everywhere same ds is there at the bottom, like, denominator side. So what I'll do, I'll take this ds to, and common I'll take it and keep it other side, multiply to other side, so it will be 0. So what I'm going to get, so I'm going to this del p, I can write del p or dp by rho, okay, and ds gone. So now we can write g dz v dv equal to 0. So dp by rho plus g dz plus v dv equal to 0. Now this is pressure term, this is velocity term, and this is some height, dz height is there. So same thing I told previously, velocity, pressure and density. Now if you see this equation, pressure is there, density is there, velocity is there, and some height is there here, dz, that is equal to 0. So this equation actually known as the Euler's equation of motion. Now first part we have completed. If you see our derivation part, Euler's equation of motion, so first part I have completed. The next part is we need to derive the Bernoulli's equation from this Euler's equation of motion. So I hope you understand how to derive this. It is very simple, but only thing is we need to remember the steps how to identify. So for Bernoulli's equation also nothing difficult. From this equation only we can identify. Okay. Now in the last class video also, if you remember, we have derived this Bernoulli's equation for vertex flow. Okay. So anyway, to derive this Bernoulli's equation, I'll use something different. Bernoulli's equation. What I'll do, just I'll integrate this equation, okay, and we can get it from there. So integration del p by rho plus integration d dz g gz integration v dv equal to 0. Integration to it. So if you do the integration on this side, you will get a constant on that. Now we need to consider the fluid flow is incompressible. Some assumptions I had told you initially. It should be steady flow, it should be ideal flow, and also we need to consider the fluid is incompressible also. Incompressible means the rho should be constant, correct? So the same thing. So what we will do, the rho part constant is there. So let's take it outside of this integration part. So what will get? Integration of dp, 1 by rho plus here also g constant, integration of dz plus, but here we will get integration of v dv equal to integration of this 0 equal to constant we can write. Okay, now what will get here? Integration of del dp, so we'll get p by rho, next g integration of dz z plus v dv, integration of v dv, that is v square by 2 equal to constant. This is the equation we are going to get. Now let's simplify this equation into more details. What will be there? What we got previously, p by rho. So what I'll do here, I'll just multiply the g term in both of the all of the denominators. So what I'm going to get, p by rho g plus here second term what is there, gz. So gz means we'll get only z because we are dividing g at the denominator. So gz will be cancelled. Now v square by 2 is there, so we'll get 2g. That is constant. Now if I write this, you can write p by rho g plus v square by 2g plus z equal to constant. Okay, so this is the Bernoulli's equation of the fluid flow. Okay, so here if you see these three terms are there. So this three term also we can you can denote this. This is the pressure energy. This is the pressure energy per unit weight of the fluid. This is the per unit weight of the fluid. Pressure energy per unit weight of the fluid. Similarly, v square by 2g. We know that we know the formula of kinetic energy, half mv square. Similarly, 1 by 2 mv square is there. But here the formula v square by 2g, we can say the v square by 2g is the kinetic energy per unit weight of the fluid. Or we can say this is kinetic head. This also can be called, or this one also you can called as a pressure head. And similarly, z is there. Z is nothing but this is the potential energy. This is pressure energy and this is potential energy per unit weight, or we can say this is potential head. So these are the terms are there in this Bernoulli's equation. So I hope you understand this equation, and some assumptions, as I told initially, these are some assumptions need to be considered, okay, while applicable for the Bernoulli's equation. This flow should be ideal flow. Okay, the ideal flow means we know that viscosity is 0. So some assumptions we can write, for ideal flow, viscosity is 0. This is ideal. And similarly, we can consider the flow is incompressible. That means rho can be constant. That is incompressible. Second part. Third part, we can say, third part is nothing but the flow is steady. That means dv by dt equal to 0. So that you can say that is a steady flow. And one more thing also it is required. The flow, the liquid flow should be, irrotational. The flow should be irrotational. So these are the terms, and the methods are there. This is assumptions part. This is the derivation part, and this is the Bernoulli's equation from the Euler's equation, and this is Euler's equation of motion. So I hope you understand the total concept of this, how to derive this one. If you are having any kind of query regarding this or doubt regarding this, you can give a comment on the comment box. Thank you all.